A couple of times, not a ton. I've had some that were annoying, but
But none like you had to, I don't know, spank them or
it's been
something.
spank them. It's been a long time since I've had anyone who was really really awful. I have had some though. All right, so this is chapter 7 on linear regression. So when we observe that the form of a scatter plot is linear, one of the natural things to do is go, well, can we come up with a model that kind of captures what's going on here? Again, remember that a model, like the normal model, is not reality. I don't think I stressed that enough in the last unit. Um, the model is this perfect. Everything is exactly even and all. It's like reality is rarely exact, which is part of why in statistics, a lot of times they're happy to give general answers. We feel that it's likely that this is happening, right? Statistics rarely says the answer is 2, right? Math, on the other hand, is the most arrogant of topics where science a lot of times uses significant digits. Math laughs at them and says, when we say it's 2 inches, we mean it's 2.0 to an infinite number of decimal places inches. And they're like, really? You can measure that accurately? And math says, yes, we can. So anyway, so the estimate made from the model is called the predicted value. Wow, this is having difficulty. And the symbol for the predicted value is this y with a little. It's called y hat.
Sound effects are actually.
Wait, that's such a
Oh my gosh, it's actually
simple
called
name.
white hat.
That's such a simple name.
Yeah.
Did the book come over that, or is that actually like what it's
I,
mathematically called?
yeah, that's what it's called. In all of
What?
statistics, everybody calls it y hat.
Because it's a Y with a hat. That's probably might be the most simple thing I've ever heard in math.
You didn't even put pepper. You gotta understand about it.
Yeah, he's ready for that pep rally.
So once we have a model, we have a predicted value, which is why when you see the equation, it won't say y equals, it'll say y hat equals, because we're finding the predicted value, not the actual value. Now, the difference between the observed value, and when you say observed, that's the same thing as saying the actual value, and its associated predicted value, so that'll be y, the actual value or the observed value, minus y hat, is called the residual. And tells you how far off the model's prediction is at that point, and it also tells you the direction. If the residual is positive, that means that the actual is greater than the predicted. And if it's negative, it tells you the actual is less than the predicted. Okay? And if you think about the word residual, the residue, it's the same thing. It's what's left over. Okay? It's the part that's left over. That if that helps you to remember this particular term. So the line of best fit is the line for which the sum of the squared residuals is smallest. It's also sometimes called the least squares line. You've used this before. You've done it on the calculator. You did it in Algebra 1 at the very latest. I don't remember if do you do any of that in Algebra 2?
Manifest fit?
Yeah,
I think so.
maybe a little bit.
Yeah.
That was back in the day.
Yeah, and they don't ever tell you where it comes from. They're just like, push these buttons and an answer pops out. I mean, basically, everybody does it, right? One of the things that, I mean, and I knew what this was for a long time, and then I saw a picture here, and unfortunately, this no longer works. Geometry Sketchpad is an old piece of software that doesn't work on the new Macs because they've changed to 8-bit architecture instead of 4-bit, and so it just doesn't work anymore. And the people who created it aren't in business anymore, so nobody's going to fix it. Sometimes I wish I was a good enough coder to go in and go, I'm going to fix this, because there are things you could use. Anyway, what it allowed you to do is it had a scatter plot, and it allowed you to move the y-intercept and another point up here to change the slope. And what you were trying to do is make these squares, the sum of the areas of these squares, be as small as possible. And it tracked that, and you could play with it, and then you could actually draw the line of best fit, and you could see how close you were to it. You can actually get pretty good after a little bit of practice. One of the things that's interesting about this, and I pointed it out yesterday when I drew a regression line, we were talking about it on the NumWorks calculator, it has to go through x bar, y bar. It's got to go through the mean of x and through the mean of y. That will always be a point on your regression line. That's something you didn't learn when you did line of best fit in Algebra 1 and you were trying to sketch where the line of best fit would be. I think that would have been helpful to know, especially if it's not a ton of data points. You could real quickly kind of go, okay, it's there, and then I want to draw a line and I kind of want it to fit the rest of the data really well. But that gives you a point to start on. It's always got to go through that point.
Is the same point always?
It always goes through, so whatever your data is, average all the x's, average all the y's, your line of best fit is going to go through that point. Which, when you think about it, makes sense.
Yeah.
It should go through the average x, average y. Okay? If you have a plot of z-scores then, remember that the average, the average x would be 0, the average y would be 0 if you have the z-scores. So it's going to go through the origin. And here's the interesting part. Its slope is going to be r. It's going to be the correlation coefficient.
Why is that?
Because once we have standardized all of that, remember we could get R by taking, what is it? And I never remember it because it's not something you ever have to do by hand. But R was, if we standardized, R was the slope of the line that best fit the data.
Okay.
That's an easier way to explain it rather than to explain the math behind it.
Okay.
So the interesting part of this is that means for each standard deviation away from the mean in x, we predict that the y value will move r standard deviations away from the mean in y. So if you're one standard deviation away in x, then you would take your r value, multiply that times 1 because you're one standard deviation away, and that's how far we think the y value will be away from the average y. So let me say that again so it kind of sinks in. If you're one standard deviation away from the average x, then our prediction is that the y hat will be r times 1. Now, since r is always less than 1 and greater than -1, that means it's going to be fewer standard deviations away from the mean. So if x is 2.3 standard deviations away from the mean in x, then we're going to predict that y is going to be less than 2.3 standard deviations away from y. From the mean in y. Because we're multiplying times r, which is always less than 1, it's going to make that smaller. So it's going to be fewer standard deviations. Okay, this property is called something that, if you've ever watched much in the way of sports, regression to the mean. And the line is called the regression line. When you hear it used in sports, it's almost always used not quite right. So the way they use it in sports, if someone has a really good game one week, the next game you can almost always predict that it will be closer to the mean, to what they do on average, right? You score 70 points in a game and that's way above your average, the next game is going to be a lot closer to the mean. And they say that's regression to the mean. That's not really what it is, but it's kind of.
It kind of just makes sense.
Yeah, it makes sense. And there was actually, I read a great article years ago that talked about guys that were, I may have told you guys this story, training, I think it was jet fighters. And if someone had a really bad day, the instructors were convinced that chewing them out was the best thing for them because the next day they invariably did better. And someone said, well, try it without chewing them out and see what happens. Yeah, the same thing happened. When someone had a really bad day, then the next day they tended to be closer to normal.
Yeah.
Okay, it didn't really matter if you chewed them out or not, which was interesting.
Yeah, it is interesting.
That's something you could talk about in your psychology class. All right, so here I've given another example. If a particular x value is 2 standard deviations away from x bar, the mean in x, the model has a predicted value for y hat, that is less than 2 standard deviations from y bar. So however much x varies in standard deviations from the mean in x, we think y will vary less than that many standard deviations. The reason for this is unless we have perfectly linear scatter plot from our data, not all the variability in y can be explained by the variability in x. So the percentage of variability in y that is explained by variability in x by the regression line is r squared. So, for example, you've got a linear model used to predict attendance at home games for American leagues in 2010. From the number of wins the team had that season, we get an r squared value of 0.284. That means that for this model, only 28.4% of the variability in attendance is accounted for by the variability in the number of wins.
What do you mean by that? Like,
So that factor, and we'll talk more about factors later, but that factor, the number of wins, only actually accounts for 28% of the variability. The attendance. Okay, sorry, let me back up and say it again. So the number of wins only has a 28% effect on attendance. There are other factors that make up the rest of that. Okay? So if you have an extremely loyal fan base, the number of wins doesn't matter nearly as much. If you have what is called a fickle fan base, where when they're winning, lots of people come, and when they're losing, everyone stays home, then this R squared value would be much higher. So part of that is it lets you know how much you can rely on the number of wins to predict what the attendance is going to be. You can have a model for it, but how good is the model?
yeah, that makes sense.
Okay? All right, so since the percentage in variability in y that's explained by the variability in x is r squared, the percentage of variability left in the residuals, meaning that they came from other causes, is 1 minus r squared. Is that really ours?
Yes, sir.
Oh my goodness.
They're from Friday and Friday.
Yep. Okay.